Hello, and welcome to Amazon ElastiCache Deep Dive. My name is Michael Labib. I'm a specialist solutions architect here at AWS, and I'm delighted to share the stage today with Brian Kaiser, CTO of Hardened, who will be presenting afterward. Now, we have a lot of content that we're going to present today, so please save your questions to the end of the session, and we'll stick around and take those questions. All right, so today we're going to be talking about the value of a key value store. We're going to dive into Amazon ElastiCache. We're going to look at the various usage patterns that you could use Amazon ElastiCache with. We'll talk about how you can scale your data using Redis Cluster. We'll look at best practices, and at that point, I'm going to hand it over to Brian. All right, so we are headed into the midst of a massive shift toward real-time data. And if you think about the need for real-time analytics, the data velocity, the data volume, it really created an emerging trend for this fast data. So in our session today, what we're going to do is we're going to talk about how Amazon ElastiCache can power those various workloads outside of caching. What is Amazon ElastiCache? So it's a managed service. It supports the two most popular key value store engines, which is Redis and Memcached. It's fully managed. So what that means is you don't have to worry about anything besides your data and the size of your cluster. It is highly available, reliable, and it's managed and hardened by Amazon. So we're going to talk about what that exactly means in a later slide. Now, if you were to think about your data as a temperature gauge, you would want that hot data to be readily available. You would want it to support extremely high request rates. You'd want it to support extremely low latency. That's where Amazon ElastiCache fits. You might also have cold data. You might also have warm data. And for those data needs, you'll have different data stores that can augment your solution. And so for your cold data, you might want to put that in Amazon Glacier, which you can archive and do something else with it. And the same thing is true for those other data stores in between. And it all depends on your use case. So I mentioned there are two popular key value stores that are supported with ElastiCache, the first one being Memcached. So Memcached has been available and around since 2003. It's been the gold standard of caching for many years. If you think about the capabilities of Memcached, it's really like a flat cache. It supports a data structure, which is a string. You can support up to 1 megabyte in that value. It has no persistence. So if you're adding shards in a Memcached cluster and you lose the data in a particular node, you lost that data. And for a caching use case, that's okay. And if it's not okay, this is kind of where Redis fits in, and we'll talk about that. Other things with Memcached, it's very easy to scale. You can add nodes, and your key space will kind of distribute across those nodes pretty easily. And it's insanely fast, right? So, I mean, we're dealing with microsecond performance. Redis, on the other hand, I like to think of as a superset to Memcached. Why do I say that? Well, it supports the string data structure. So you can have the string value, except from a 1 megabyte. Instead of having data up to 1 megabyte, you can store up to 512 megabytes worth of data. There are other data structures, which we're going to dive into. It has persistence. So if you care about that data and you want to have support RTOs and RPOs, you can do that with Redis. And we'll talk about the different options you have. It's highly available, so you can have a master. And if that primary node fails, you can have a read replica, which will be promoted to be the new master. It's very powerful. There's over 200 commands in Redis. You have Lua scripting, which you can build some business logic, and you can have that logic execute in memory. And it's also simple. And that's important to mention because syntactically, it's very easy to use. And we'll see some examples later in this presentation. So when we talk about data structures, I like to start with the basic. So the basic data structure is a string. Now, in Redis, this is supported both in Memcached and Redis. In Redis, it supports up to 512 megabytes. It's binary safe. So what does that mean? What it means is you can essentially put anything that fits into that space in that value. That could be HTML code. It could be a JSON object. It could be an image, a picture. And there's also a cool capability where if you have an integer representation in that string value, you can increment and decrement that value and use it as a counter. Where it gets interesting with Redis is these additional data structures. The first one we'll talk about is a set. So if you remember, if you came from a dev background, a set is a collection that allows you to have unique values or elements within that collection. So say, for example, you have a customer. You want to group maybe your customer IDs. Your key may be that the customer list, and in every value that you have in that set might be a customer ID. Now this is great. Why? Because you don't want to have duplicate customer IDs. So this is managed for you in memory. It's lightning fast. It's microsecond performance. And it's a great way to group your data together. Now, a sorted set is a set, so it maintains those unique values within the set, but it also has an interesting parameter, which is a score. Now, a score allows you to sort the data based on a particular value, right? So take, for example, you are building a game, and your key might be a leaderboard, and then your users are the value, and you want to sort these users based on something, right? So in a game, you're actually sorting them by the score. So again, this has happened for you in an in-memory performance engine, and you pass in those values. It'll maintain the uniqueness, and it will sort it for you automatically. And then you can retrieve it in a number of ways. One way that you can retrieve it is in a synchronous order, in a reverse order, and you can pull in a range of information. So again, this is great for deduping information, for grouping information, and sorting information. And we'll take a look at other use cases where you can use a sorted set. A list is a collection that allows you to capture the elements that are inserted in that order. So there is no particular order that this is maintained, but it's great for pushing and popping elements either from the head or the tail of this list. So a lot of common patterns that are built using a list could be a timeline. And so you can have a timeline that might be your key. And all the elements that you put in that list could be an event based on that timeline. So this is a common pattern and a usage for a list. And then hashes, they are my favorite. So what a hash allows you to do is it's a data structure that is suited for object representation. So take, for example, you have a customer record. Now that customer has attributes. That attribute could be the customer name, could be a customer address. So if you're using a hash, the key may be your customer ID, and then all the fields and values associated with that customer are the attributes related to that customer. Now why is a hash cool? You can create a JSON object, and you can store this in a string. But what I like about hashes is that you can do operations on individual fields. So you can set the data in a hash. It's memory efficient in Redis. And then I can query individual elements. So maybe within my customer key or my customer list or my individual customer, I just want to know his address. I can just query for that individual field. So it's great. One of the questions that I get a lot from customers who are new to caching is which one should I use, Memcached or Redis? And so one of the things I like to do is kind of think backwards. If you are just doing a caching use case, and I like to start with what languages are you using? You might be using a language that has sophisticated support for Memcached. Maybe it's baked into the framework. And if you're just using caching, maybe Memcached is good enough. However, if you are needing to do caching, but you think that there might be other use cases for your data, I'll tell you to use Redis. I think Redis, in a lot of ways, does what Memcached can do, but it can support additional use cases, and we'll take a look at those. So some of the value propositions that you get with ElastiCache, I mentioned the first one, it's fully managed. What does that mean? You just have to worry about the data that you put in a cluster and the size of your actual cluster. As far as patching, as far as failovers, all those additional processes, which we call heavy lifting, it's kind of removed from your plate. The other thing is that it's open source compatible. So if you already have code written using Redis on EC2, You can easily port that code over to ElastiCache. Same is true for Memcached. So we support all the open source protocols. There is no cross-AZ data transfer. So this is sometimes overlooked. So say, for example, you're running Redis on EC2, and you're in a multi-AZ environment. You may have your nodes communicating with each other. And if you're doing that, there's an additional charge. So if you take a look at the actual charge for your EC2 instance, plus the data out, you're in the same ballpark of using ElastiCache. Might as well just use ElastiCache. And this is especially true when your node size or your cluster size is large. The other thing is that the enhanced Redis engine comes with this. And so I'll talk about that in the next slide. And this is really some of the lessons learned that we've heard from our customers that we built into the service. So the first one, the first feature is that we've heard from customers that memory management can be challenging with Redis. So one example is, say for example, you're running Redis and you have background processes like doing snapshots and syncing, especially with snapshots. Depending on how much writes you have occurring on the primary, Redis may take up to, it may double your memory footprint on that instance. And if you don't have enough memory for those background processes, they'll throw you into swap. Now, you don't want to be in swap when you're in an in-memory database system. So what we have is we have enhancements that detect that situation. We'll look at how much memory you have available on your instance, and it will put you in a forkless backup scenario. The other one is write throttling. So if you have a lot of writes hitting your primary, we've heard from customers that this could be challenging because your read replicas may fall out of sync. And so we have controls that will detect that scenario, and it will throttle some of those writes to make sure that your cluster is in sync. The last one that I'm going to talk about is a smoother failover process. So say, for example, you have a primary, you have a replica, actually you have a couple replicas, and then your primary fails. One of your replicas will be elected to be the new primary, but any other replica that you have, the data will be flushed. And this is if you're running it on EC2. What we have is we've kind of enhanced that process to make sure the whole failover process runs smoother. So we don't flush the data in the other replicas. We just make sure that it's in sync with the newly elected primary. Let's talk about some usage patterns. The most popular one is caching, right? So there's a couple reasons, a couple drivers that you want to do caching. The first one is you want to alleviate some of the pressure to your database. Now that pressure could be maybe your database can't scale. It doesn't matter what your database is. It could be Cassandra, it could be DynamoDB, it could be Mongo, it could be RDBMS based database. It could be anything. The other reason, the other driver is maybe the performance that you're getting out of your database isn't good enough, right? You want to lower that latency. Well, in a few lines of code, you can augment your architecture and add a caching layer, right? And so what that caching layer is going to give you automatically, it's going to give you a higher level of throughput, up to 20 million reads per second, up to 4.5 million writes per second. That's crazy. The second one is it's cost effective. Why do I say that? Because if you were trying to scale your database, a lot of times the cost of scaling your backend database, which you'll never get the lower latency compared to a caching system, the cost of scaling your database is a lot higher than adding a caching layer. And then the third one is better performance, right? You're getting microsecond speed. And in today's day and age, you want to have that fast response times to power your applications. Now, if you're using DynamoDB, what's cool about this is that you can have an automatic trigger, which is automatically gonna populate the data in ElastiCache. So you can have a trigger based on an update that's hitting your DynamoDB table that will put that update in a DynamoDB stream where a Lambda function will be triggered off of that stream and then populate your data into ElastiCache. Now, outside of caching, this is great for decorating your data because you might not want to put that data in ElastiCache in the same way that it's stored into Dynamo. You might want to augment that data. You might want to enhance or enrich that data, and you can just code that into your function. Now, once you set this function, it's just there. It's just going to work for you. This is a way of a write-through pattern. Now, I said earlier, in a few lines of code, you can augment your solution by adding a cache. Let's see if I'm lying. So from a write-through, if you see there's 2 lines that are highlighted here. Essentially, how a write-through works is you are writing to your system of record, to your database, and after you write to your database, you immediately write that data to your cache. Now, what's great about a write-through pattern is that you are proactively filling your cache. You're hydrating your cache with data that you think is usable. Now, the con with doing this is that you have the potential of putting data into the cache and using more memory than you probably need. On the other hand, there's another common pattern that's lazy loading. So the way lazy loading works is you check your cache to see if a value is there. If it is not there, you retrieve it from your system of record, your database, and then you set that data into your cache. Now, the value with that is that you are setting the data that you know your application actually needs, right? So the con is you have a higher chance of getting a miss, which is, the data is not in your cache, and that might not be best for your performance. In practice, people typically use both of these patterns, and they augment with a TTL, an expire parameter, based on the data frequency, the change of their data in their database. So you have to understand how your data changes in your system of record, and then apply a TTL that corresponds to that data. Okay, so we're talking about caching. Another example I'll quickly go over is session caching. Now, when you're in a distributed environment, you have web applications, it's important to abstract your sessions and put them in a distributed cache. Right, so this is great, especially if you have a fleet of servers that can grow and shrink based on your usage. So based on a lot of the frameworks that you're using, say for example this PHP example, I can augment my solution with just changing a couple configuration changes. And I don't have to create a session manager or do anything else. I could just make these changes, and now my application is using, in this example, Memcached. This is also true for Redis. And it's also true for a variety of programming languages. So this is just one example. You could take a look at that GitHub repo for how you can actually do this. IoT is an emerging kind of need that we're seeing with customers. So imagine you have a solution that you have devices and you're capturing, say, sensor information. One of the ways that you could do this, there's a variety of ways that you could do it, but one of the ways that you could do it is you can create an AWS IoT rule. That rule will trigger a Lambda function, and then after that Lambda function is triggered, you can have whatever sensor information that's coming in, you can have that basically persisted into your Amazon ElastiCache engine. Now, why is that good? It's good because you're not paying for request rates, you're not paying for throughput, you are not paying for anything. From a cost-effective perspective, you're only paying for that instance type that you've selected, and you can support the 20 million reads and the 4.5 million writes per second. That's fast. That's going to support all your device data. Now, say, for example, you want to capture that data in another repository. Maybe you want to have longer retention. You can always augment your solution and dump that data in DynamoDB. You can also create a data lake, put that data in S3, and then you can do EMR jobs on top of that data, or you can archive that data into Amazon Glacier. If we look at this particular example for the IoT rule, you'll see that it's pretty simple. This is a Node.js example. I actually have the code checked into GitHub as well. You can play around with that. But the Z-add is essentially how you add data to a sensor, to a sorted set. So the sorted set is called sensor data. And the date is my score. So we talked earlier about what a score does with Redis, with a sorted set. So what I want to do here is I want to capture time series data. And it's important for me to have the actual time or the date of when that event actually occurred. Now, when I query this data out of the sorted set, I'm going to do the reverse order, so I know all the values that happened in the most frequent data that I'm going to have that return back to me. Now, the HM set is how you persist data into a hash. And the first value is my key. So the device ID is my key, and all those additional attributes and values are the fields and values that I have associated to my hash. Now I'm wrapping this into a multi-command because I just want to queue up these commands and just execute that transaction with Redis. Another popular use case is streaming data. So we have Amazon Kinesis Streams. And with Kinesis Streams, you can have a AWS Lambda function trigger as soon as records are in that stream. And then, as I mentioned earlier, as that data is coming out of that stream, you can decorate that data, you can do something with that data, and then you can persist that data into Amazon ElastiCache. Now, you can always have an EC2 instance sitting on the right-hand side here that can query ElastiCache. Maybe you just want to see that moving data moving. Maybe you want to do something with that data. You can always do that. And the same is true as I mentioned before. You can always augment that solution and store that data in another system of record. Streaming data enrichment is another interesting pattern that we're seeing customers use. So imagine you have that data coming in the stream. Now, you may have various data sources that are populating that stream with data. That stream is a raw stream, and it might not be a cleansed stream. So you want to do something with that data before you start using it. So what you can do is you can collect that data from the stream, have an AWS Lambda function trigger when records are in the stream, persist that data into Redis. Say you wanted to dedupe data, you can throw that data in a set. Say you wanted to decorate that data, you can take data that's already persisted into Redis, and then based on the records that are coming in, you can decorate that data, you can enrich that data, you can do a lot of things with that data. And then once your data is cleansed, throw that data in a cleansed stream. And then you can run any type of operations on that stream. You could even do SQL on that stream using Kinesis Analytics. Spark streaming with Redis is an interesting use case. So, typically when you are doing data analytics, you have maybe data coming in from Kinesis Stream. You have maybe a Spark streaming job that's pulling data out of that stream. It's summarizing that data, it's augmenting that data, it's dumping that data into S3. Then once it's in S3, your data lake, you could have maybe a Redshift or another EMR job pick up that data and do something with it. Now, what's an interesting trend here is that if you augment your Spark job with Redis, you will, by orders of magnitude, speed up that performance. Why? Because number one, pulling data out of an in-memory system is faster than pulling data from a file-based system, right, or a SSD-based system. The second reason is that if you think about the kind of code that you typically write in Spark, you're usually sorting data, you're aggregating data, you are doing some sort of function that a lot of these advanced data structures in Redis can help reduce your code complexity. So from both angles, it's an interesting project to take a look at. So Redis in a multi-AZ environment, let's take a look at that. So the first thing that I'll call out is this is in a non-clustered environment. So we'll talk about clustered environments a little later in this presentation. But typically what happens is you have writes that you want issued to your primary. Your primary is asynchronously communicating to your read replicas. Now there's an option to set for multi-AZ, and when you do multi-AZ, we will put your read replicas in different AZs, and we'll enable that failover. And when a failover happens, we'll basically take the DNS name from your primary, and we'll propagate that to one of your read replicas. Now we'll select the read replica that has the lowest replication lag in your cluster. Now, one thing that we always recommend as well is that when you do snapshots, do them on a read replica so you don't interrupt your master, or your primary. Let's take a look at that. Let's visualize it. So you have your applications. They are talking to your primary, which has a border around it. Something happened to that primary. DNS replication will happen. The read replica will be the new primary, and then we'll replace that replica. And in this particular example, you'll see there's another data store. In this case, it's DynamoDB. It is showing you that your application can talk to a variety of databases. It doesn't really matter, but the databases themselves don't talk to each other. Now, one question that I get a lot is, how do I know what my read replicas are? Especially in an environment where your read replicas can change. Well, we provide an API that allows you to query your replication group, and you can pass in a replication ID You can easily get all the attributes associated to your cluster, and then once you have, for example, your replicas, you can use them, right? So you can issue reads against your replica and take advantage of them. So an example of how you could do that, I've checked into that GitHub repo. All right, so what's new? So 2 months ago, roughly 2 months ago, we announced a new feature, which is Redis Cluster. We support up to 3.5 terabytes in Redis. We, as I mentioned earlier, up to 20 million reads per second, up to 4.5 writes per second. All the enhancements that we talked about earlier are rolled into this version. It's up to 4 times faster than version 2.8, and that's because it's not based on DNS, and we'll talk about how it actually works. Cluster level backup, you don't have to back up individual nodes, and we support up to 15 shards within your cluster. The other thing that I'll mention is fully supported by AWS CloudFormation, if you're familiar with that. It's a template engine that allows you to build environments, and it's supported in all our AWS regions. The other thing is that there's 2 additional data types that are supported with version 3.2. One is the bitfield command, and then the other one is geospatial. I love geospatial. I think it's awesome. It's an awesome way to build data-aware code or geo-aware code. So say, for example, you have a mobile application, and in that mobile application, you want to advertise particular points of interest to your customers. Those points of interest could be anything, right? They could be restaurants, they could be anything that you really want to advertise. Well, in that mobile application, you can pass up the longitude, latitude of that position of that customer, and based on geo ads, which are those points of interest that you added in the cluster, you can find all the points of interest within a particular radius, right? So I can say, all right, this customer is in this particular location. Let me find everything in a mile away from this customer. And then let me send those recommendations up to this mobile app so we can see it. Now, again, as I mentioned, Redis is an in-memory system. We're dealing with microsecond performance. This is why this is awesome, because realistically, when you have an application like that, you want to be able to market those advertisements as quick as possible. Now, in addition to finding all the points of interest within a particular radius, you can also do other things like what's the distance between 2 points, as well as other things. Scaling with Redis Cluster. So how do you tell the engine that you want to horizontally scale? The first thing you do is you check cluster mode. Otherwise, if you don't check that, we'll assume that you want that primary and then that read replica kind of vertically scaled architecture that we looked at earlier. And before we kind of dive into how sharding looks like, let's talk a little bit about the client. So essentially, the way sharding works is you have 16,384 total hash slots. Now, those hash slots are distributed across your shards. Now, by default, that distribution is an equal distribution. So if you create 5 shards, those hash ranges will be distributed across those shards. Now, your actual client, now your client being the driver or the client code that you're using to connect to Redis, has a map of every shard that has those hash ranges, as well as any read replicas for that individual shard. Now, what's also great about a client is that a lot of clients they load balance reads for you. The other thing that I'll mention about the client is that because all that information is in a map within the client, you don't need DNS propagation. All those IP addresses and all that cluster information is built into the map. And so the client itself knows where to route the traffic. Now, this, of course, is much better than doing things like a proxy or something else. Why? Because that map is right there with your code. And so you can you're talking directly with the cluster, and you can eliminate any other network hop between your code and the Redis engine. All right, let's visualize this. So the outside blue border is your Redis cluster. Now, that cluster, again, can be up to 15 shards. In this example, we have 3 shards. The nodes that have the gray border, those are your primary shards. Now, any other node that has the same range, in this example, is a read replica. So our first shard has a slot range of 0 to 5454. And then you can see which are the read replicas. In this example, they're in different AZs. And I have 2 other shards with a different hash range associated to them. Now, with ElastiCache, you can have up to 5 read replicas for each shard. And as I mentioned, up to 15 total shards. Every one of these nodes together are your total cluster size. So in this example, we have 9. How do you do that, right? So in the console, the first thing that you do is you give your cluster a name. So in this example, my Redis cluster. The second thing you do, you select the engine type, 3.2.4. Then you are selecting a node size. This is the node size for your shard. So in that case, 13.5 times 3, that's the total memory space for my cluster. And then I'm saying I want 2 shards, or 2 replicas for my shard. So in total, there are 9 total shards. Now I mentioned earlier, by default, we'll assume you want equal distribution. So we have the total hash slot range, and we will divide that range across each individual shard. But you may have a key or something that's a hotkey. Say, for example, you're always reading from an individual key. So we'll give you the capability to change the slot and the key space orientation of your cluster. And it will also, by default, spread your nodes across AZs, unless you have a particular use case where you want your nodes in a particular AZ. Let's look at failure scenarios. So assume that your primary fails. This is an easy scenario, right? So what we do is we'll promote one of your read replicas to be a new primary. Your previous, your primary will be a read replica, and we'll repair it. Your client code, your client is aware of this, and this typically happens within 30 seconds. As far as your reads, there's no interruption. Assuming you have read replicas, your application can continue reading from the cluster. You might have some write interruption in the process of making that new read replica the new primary, but that's up to 30 seconds. Another example is when you have 2 primaries fail within your cluster. And in this example, or 2 or more primaries fail in your cluster. In this example, we have 3 total shards. So 2 primary shards are failing, and why this is challenging is that if you're running this on EC2, and we've heard customers tell us this, if the majority of your primaries fail, it causes a problem. And why does this cause a problem? Because you need a majority of primaries to be available to elect new primaries from read replicas. We have controls around this. So essentially, we'll see, we'll look at your entire cluster health. And if you're in a scenario where you don't have the majority to elect new primaries, we have controls that can resolve that problem built in the engine. You don't have to do anything. We will do this for you. How do you get from a non-clustered environment to a clustered environment? So it's pretty easy. Essentially, you take a snapshot of your cluster, and then you restore that snapshot on each one of your individual shards in your cluster. Now, the way cluster works, there's a particular hash range, right, that we mentioned earlier on each one of these shards. So we'll discard any keys that aren't applicable to that hash range. Now, if you wanted to, migrate from a non-clustered to a non-clustered 3.2 version, that's seamless, right? There's a couple clicks, and then that just works. The other thing that I'll call out is that it's important to make sure that your client supports Redis cluster. And so you can just look up the client that you're using and just make sure it supports Redis 3 and up. CloudFormation is fully supported out of the box. So essentially, building your cluster, how many read replicas you want, all that is supported. So you want to augment or automate your environments, maybe build up an environment for test and dev, and then just terminate it. You could do all that through CloudFormation. Okay, so best practices. Kind of go through a few of these so we can leave time here in the presentation. These are just a few that we snuck into the presentation. The first one is avoid really short key names. So I know a lot of people who are, they try to be extremely memory efficient. They want to have like the smallest, abbreviated key name possible. So what they'll do is they'll pick a key name that doesn't make sense for an application developer, right? So pick something that has a logical schema name that's easy to code against. The second thing is, use hashes, lists, and sets when possible. These are memory efficient collections. So one thing that you can easily do, so if you think about it this way, if you had maybe 5 keys and you had a hash that had 5 values in it, the hash has a smaller memory footprint than those 5 individual keys. And then the last thing is I see some people, they have a keys command coded into their application. Don't do that, right? That is that's a blocking command. Instead, use like scans and just kind of iterate through that, the results that you get. All right, so a few things. I talked about a lot of these things. I'll just kind of mention a few of them. From a Redis cluster standpoint, have an odd number of shards. Now, I talked about earlier that even in a situation where the majority of your shards fail, we will fix that scenario. We have controls around that, but it's still good to have an odd number because it just speeds up the overall failure scenario. The other thing is, for critical workloads, you want to have a few read replicas, associated. For swap usage, you'd never want to see that. You never want to be in swap memory. So you always want to see that at least 0 to very low. And let's see what else. For reserved memory, I mentioned if you're running this on EC2, that typically this can double your total memory footprint. With ElastiCache, we'll just recommend 25 to 30% reserved memory, just to make sure there's additional memory for those background operations in Redis. A few things I'll call out here are some CloudWatch metrics. Now, every CloudWatch metric, you can have an alarm set up. The first one, CPU, typically don't go past 90. Remember, Redis is single-threaded, so you want to divide that by the number of cores that you have. Swap usage, low. Again, this is an in-memory system. You never want to be in swap. Cache misses the hits. You want to have more hits, right? So if you're getting the value out of your cache, you want to be finding data in the cache. Evictions, this is when Redis or Memcached kind of just jumps in and starts evicting keys because your poor memory management. You never want to really run into evictions unless this is unintentional. Maybe you're following a particular algorithm that, like the Russian doll caching algorithm where you want to do this. I wouldn't recommend it. There are eviction policies that you can, look at. And I would select one in the case you are in an eviction. Select one that makes sense for your application. The other thing I'll mention is for for the clients, you can have up to 65,000 connections per node. But it's good to have parameters around timeout and TCP keep alive to make sure you're killing dead connections or idle connections. Just get rid of those. And that's pretty much all I'm going to cover for this session. The other thing, just to kind of recap, Amazon ElastiCache supports a variety of use cases. We're not talking about just caching, although that's what the name kind of sounds like. We're talking about a lot of use cases that support that fast data and fast-moving data. The second thing is, as you saw, with a few lines of code, it's very easy to augment your solution. Whether you're using Memcached or Redis, doing lazy loading, write-throughs, very easy. A lot of frameworks already support these caching solutions. So in some cases, it's just configuration changes. And then lastly, you can support terabytes worth of data with millions of IOPS. So to really power your architectures, it's an interesting, it's an interesting and also a high ROI to augment that solution with putting ElastiCache as part of that. Thank you, guys. That's all I have for this presentation.
All right, thanks, Michael. Hey, everyone. My name is Brian Kaiser. I'm the CTO of Huddle. So today I'm going to talk about what Huddle is, kind of how we got into basic caching, our journey from Memcached to Redis and ElastiCache, and then some best practices we learned along the way. So Huddle is a sports platform that really allows coaches, analysts, and athletes to win with video and analytics. We were founded by myself and 2 partners about 10 years ago, really focusing on football at the professional level. Nowadays, we work broadly across sports, from soccer, basketball, football, from kind of peewee and youth teams, all the way up to the NBA, NFL, and English Premier League. In fact, over 98% of American football teams use our product, and the entire English Premier League calls us a customer now. So it really is broadly applicable both domestically and internationally. This is just a cool example, I think, of some of the more advanced analysis that we're seeing the English Premier League do around player tracking data. They're really kind of cutting edge in the space of sports analytics, as you probably read about a lot online. So some quick fun facts on our platform. We have over 130,000 teams internationally using the product. And that equates to over 4.5 million active users. We actually store and serve over 2 billion videos on S3. So needless to say, we have a lot of video, and S3 really likes our usage. We actually ingest and encode over 35 hours of HD video per minute during our primary sports season, get that encoded and served back out. And we're servicing over 15,000 API requests per second during that same time span. And every one of those API requests is actually multiple cache hits, as we'll kind of talk about. So we've been on Amazon pretty much since the start of Huddle. And in fact, if you look at the dates, it's the start of Amazon is right about the time that Huddle actually started. And it really made sense for us, right? We needed the ability to scale very quickly. We handle very seasonal traffic workloads, which is a great fit for Amazon. And we needed the ability to deliver high performance to teams no matter what region of the world they're in. Amazon checked all those boxes for us. We run a fairly standard microservices architecture at Huddle. So we use an ELB as our primary entry point. That's actually spread out to our routing layer, which is really Nginx boxes in each availability zone that talk to Eureka. And Eureka is a service discovery system written by Netflix. It's a wonderful piece of open source software. And we use Eureka to see what services are online, what servers are available, and what routes we need to do, and then route down to the appropriate squad cluster in the microservice cluster in each applicable availability zone. Now, the entry point to that is, of course, our web tier. Pretty standard. We run IIS for our primary web server, and it's just an auto-scaling group across the 3 AZs. Each squad is able to determine the supporting services to meet their needs, whether it's ElastiCache, DynamoDB, SQS, whatever it may be to actually service their needs. Each squad is able to use those Amazon services. And then MongoDB is our primary data store at the bottom layer. Now, we've had caching for a long, long time, and we got started with Couchbase on top of Memcached. And honestly, it was a pretty logical fit for us. Hopefully, it's obvious from this presentation what Michael's talked about, that caching is easy to implement and it's very high impact, and we recognized that early on. And honestly, for us, it's not just about performance. It's also about some of the things that are a little less obvious. So we noticed that it helped us smooth out volatilities and things like EBS latency that might spike or network blips that happened in our internal infrastructure. We also found it was a very effective way for us as a smaller startup to scale cost effectively without having to increase our database usage significantly. We started making the transition to Redis a couple years ago, and it's been quite impactful for us. I like to think of it now as kind of the Swiss Army knife of our infrastructure. Not only can it do that very basic key value store, but it also has so many advanced capabilities and data structures. We use it for queuing and PubSub. In fact, now we serve over 80,000 requests per second through our Redis clusters. And in preparing for this presentation, I did some calculations and found that our average latency is less than 1 millisecond, which is pretty astounding, right? It even surprised me. And that's 1 to 2 orders of magnitude quicker than what we found from our traditional database fetches. So now I'm going to walk through some kind of basic use cases of how we use Redis at Huddle. I'm going to start with the most simple one, which is the lazy loading basic data caching. Now, we put this data caching at the lowest level possible, right in front of the database calls in the database functions. And we do that to allow for very easy cache invalidation. We found that if our caching code was spread out broadly or up at the service layer, invalidation became very difficult. So in our opinion, we like to have it as low as possible for those invalidation. So here's a very basic get utility function that we wrote, and this is in .NET code. One of the things that I think is somewhat unique is the first chunk, where it says _Redis enable.value. Huddle has a system of feature toggles where we can turn on and off different pieces of our system and architecture dynamically on a per cluster basis. So for example, in Redis, if we need to do maintenance on a certain cluster, if we're having any kind of connectivity issues, we can hit one toggle, and we actually use SNS for this propagation, and we can turn off Redis access across that entire cluster. Now we have some pieces in our system that are extremely high volume, and just kind of turning off Redis binarily would cause the thundering herd effect potentially and a massive load on our database. So in those cases, it's much more of a broad range toggle where it might be between 0 and 100. We can ramp up and down our usage of these features depending on the maintenance and the time of day, things like that. The next line you see in bold there is just where we actually get a value from the database. This is coming back as a byte array, very, very simple, and then we're deserializing it in the bottom line. In this case, we're using protobuf. So we're taking that byte array and we're deserializing it into a .NET object. Again, this is incredibly simple, but I just want to show how simple this actually is, and this is the code we use for it. On the flip side of it, here's our put method. So you can see, again, that toggle at the top that allows us to control access to Redis. We actually serialize the object into a byte array, and then we pop it into the database with a TTL on it. In Huddle, it really depends on what the frequency of access on our objects are. It could be anywhere from 5 minutes to an hour on the low end, up to 1 to 7 to 30 days for the amount of time that we put objects in the cache for. A slightly more complicated example is a utility function we wrote to kind of enforce this lazy loading pattern. So this is our get and put. So again, we have the toggle at the top. We go to attempt to get that key out of cache. If it's a cache hit, we go ahead and return that value right away. If it's a miss, we're able to pass in an accessor function, which may be a DB access or maybe a call to another microservice, and then we put that cache key in. Again, this is ultra simple, right? We write these functions to help enforce a good pattern and make sure we don't have any problems or bugs down the road. So what are some examples of ways that we use this? Well, the most common one for us is the auth token. So every call that comes into Huddle gets authenticated, right? That auth token is in the cache. We check it every single time. So these keys alone are over 15,000 requests per second just for our auth tokens. The next big one is user information. This is a perfect example, as Michael mentioned, of where a hash is a wonderful fit in Redis. We can store the relevant information for a user, like their jersey, their email address, what teams they're a part of, in a simple hash function in Redis, and either get that whole object out, which is actually the most common thing for us, or individual pieces as we need it. Likewise, we store information on our teams. This might be the sport they're a part of, the level, whether it's a high school, collegiate, or pro team, in a very simple hash function in Redis, and it just makes a whole lot of sense. So let's move on to a little more advanced example. This is our news feed. So you can think of the news feed kind of like, well, a Facebook news feed, right? This is a central source of information for our users and teams. And a good example would be a coach posts a new highlight reel or playlist or video for a team to watch, and you can imagine it populating into the news feed. This is a function that makes incredibly heavy use of Redis for us. In fact, it's such a heavy user of Redis that if Redis has a problem or goes down for any reason, we have to turn off this piece of functionality in our system because it would quickly overload our database. And I think it'll make sense in a second when I talk about the access patterns. So at the top of the page here, we use a hash. So we're storing things like the background image for the team, the location of the team, things like the view count for this page or for highlight reels, and the number of followers of this team. And again, this is a wonderful use of a hash. Often, as an example, in this page load, we're retrieving that entire thing out, but we can atomically increment things like view count and followers, right? It's a very, very simple but highly effective and highly efficient way of storing this data. And kind of the bulk of the page here is the actual feed itself. And I think this is a somewhat novel approach that one of our developers came up with for this. Essentially, this is a single Redis list of feed IDs and a little bit of metadata around them. And what happens is, let's say a coach in that previous example is publishing a video. We will go through every single user on that team, and we will push that ID and information onto the Redis list for that user. It's a very, very quick operation, and then we'll trim the list to make sure it's at a constant length. And so in our case, we keep this list at right around 500 items. Now, when the user is scrolling through this list, we know the offset. So we can actually grab a range off that Redis list of the IDs and information, and then we can hydrate that with those items out of the cache in parallel with a multi-get. So I know that's a lot there, but effectively what that means is we're able to generate this news feed in literally a couple milliseconds on page load. It's a very, very efficient operation for us for something that would be very complicated, right? And this is a wonderful example of how we can use lists and coupled with a caching and a multi-get. So let's talk about another example, distributed caching. And this is kind of a dirty word often. I don't encourage you to use distributed caching, but when you need it, it's really nice to have a very reliable and consistent way to do it atomically, and Redis provides that. So in this example, we have a lot of coaches. They're at their game, and they're filming it with iPads. Fragments of this video is flowing directly to S3, so little snippets of the game live while it's happening. We're then making calls into a queue, which get put into a very massive worker farm we have that does that video encoding. We talked about that 35 hours of video per minute, right? That's where these jobs come in. We're grabbing those chunks of video, we're encoding them in multiple qualities, we're sanitizing them, we're getting ready for streaming. The challenge comes, this is all happening in parallel at a very broad scale. So these jobs come back, not only are we writing them to MongoDB out of this queue, but we also have to use a distributed lock to make sure that we're coordinating delivery and finalization of this video. And it's a small piece, and it's very, very quick, but it's incredibly important to get right so that we know when this video is ready for the user. And that's what we actually use ElastiCache for. And again, this is a thing that ElastiCache does extremely, extremely well in our experience. And if you have to do distributed locking, I'd recommend you checking it out. So we've got to answer the question, why do we use ElastiCache versus just running Redis ourselves? And Michael gave some great examples of the benefits, and I can tell you from personal experience that we've seen that. For us, it's also an operational question and an operational answer. So we are organized as a company and a product team like Spotify. We pretty blatantly ripped it off, and I appreciate all the documentation they've done on this. In fact, these are screenshots from a slide that they've posted online. And what this model is, it's all about tribes and squads and pushing down decision-making and autonomy as low as possible. And that includes not just requirements gathering and working with customers, but also the operational side, whether it being what services you want to run, how you want to run the servers, monitoring, scaling, and all that. So having a managed service like ElastiCache is really critical to allow our squads to operate autonomously. And it's a perfect fit. Each squad can determine how they want to integrate that into their cluster. Do they want to use Redis cluster? Is it a single node? What size do they want it to be? What eviction policy makes sense for them? And how do they want to manage their serialization? And ElastiCache takes care of all the operational complexity, and it just works, and they can focus on how they actually want to use that service on top of it. It really just makes sense. So we had an analogy when we were prepping for this where someone said, it's kind of like a slam dunk, isn't it? And that's a cheesy sports analogy, but I think it really resonates here. So I'd be remiss if I didn't talk about Redis cluster briefly. This is a really new addition. It's been incredibly impactful for us. I'll tell you that we don't need to use it broadly. It's kind of like a hammer, and often it's overkill for us. But where we do need it, it's incredibly important. And it was the last piece of the puzzle for us to migrate all of our caching onto ElastiCache. I gave just a screenshot up here of that feed that I talked about earlier. That is running on Redis cluster in production today, and the performance on it is really incredible. This is one screenshot that I took just prepping for this presentation. So this is one single shard out of that feed cluster. And you can see it's running right around 1.2% CPU, and it's doing 100,000 operations per minute. I wish that was per second, sorry, but that's per minute. But on this single shard at 1.2 CPU. I mean, that's really, really incredible. We're not even pushing this, and we're operating in shard capacity. All right, so it's time for me to wrap up. I want to talk about some best practices that we've learned over the past couple years on ElastiCache. First and foremost, and I cannot stress this enough, if you're in production, use a multi-easy replica. Honestly, you just have to. At the end of the day, you're running on an infrastructure where nodes need maintenance, nodes will fail, there'll be network problems, and in our experience, running multi-AZ has been a very, very efficient way to provide uptime. Our failover is often in the order of magnitude of seconds. I know they talk about 30 seconds. For us, that's been a very high bar. It's often much, much quicker than that. Multi-AZ is critical. Now, obviously, in dev and test, we run single node, right? But production's always multi-AZ. Michael had a slide up there that he went through kind of quickly, talking about setting up alerting. That's been critical for us. And early on, we didn't do a very good job with this, and we paid the price for it. So some of the alerts that we found very valuable, swap usage. We've had some cases where we didn't manage our memory properly, swap usage got out of hand, and all of a sudden you see horrible performance. This is a very critical alert to set up. CPU and evictions are the two others I'd recommend alerts on from our point of view. So very important. I think it's worth taking the time to understand available eviction policies in Redis. Depending on your use case, different policies make sense for you. There's 6 of them out there. There's a really, really good documentation online, so I don't need to waste your time talking about it. But for example, there's one called All Keys LRU. And if you're just going to have a cluster that only does caching, it'll take care of the eviction for you based on least requested automatically. You basically don't even need TTLs. It's a very easy way to phase in. Whereas we use volatile TTL for clusters that we have mixed things, like we have some distributed locks, some caching, some more persistent objects. And if we use the wrong one, we might get the wrong objects evicted from memory, or the wrong access patterns might be evicted. It's very, very important to get that right. My final one, it's worth the time to learn and understand Redis's advanced data structures. I talked a little bit about our newsfeed. When we first got into caching, we were just doing the basic object caching, key value. And that is impactful, and it makes a huge performance difference. But what really happened in our company, it was almost like a cultural shift to take the time to learn to understand sorted sets, hashes, lists, hyperlogs, and how those could benefit our ability to provide higher access to our data for our customers and things that just aren't possible in a traditional database. It really kind of opened our eyes to what we could do. I also think it's important to understand the big O complexity of the operations on those data structures. So when we were looking at designing the newsfeed, we had to decide, did we want to use a sorted set based on date, or did we want to use a more traditional list? Well, we looked at the big O complexity of the operations we needed to run on that object to understand what the performance implications are. And again, this is all documented on the Redis site very, very clearly. There's wonderful examples on there. I encourage you to check it out. So with that, I really appreciate you talking to me today. I'm going to be available afterwards to answer questions. I encourage you all to fill out the recommendation forms. Thank you and have a good one.